Okay, in this video I'm going to talk about the Young double slit experiment, and I'm just going to do the actual geometry that was used in the experiment and figure out how the things in the experiment relate to the wavelength of light. So first of all, we need to remember that what our conditions for constructive and destructive interference are. So L2 minus L1 is equal to n minus 1 lambda. That gets us back in phase or back in step with integer wavelengths. So that's our constructive interference condition. L2 minus L1, n minus 1/2 lambda. That gets us a half step out of phase, and that creates destructive interference. So really, what we need to do is figure out how could we measure L2 minus L1 in this setup. So I'm drawing this obviously way out of scale, much bigger than it would be, so that I can show you what's going on in this experiment. So here's our light coming in, and we're resolving it into two sources here by having two openings, and those are going to a screen that is far away. The distance between the screen and the sources we'll call L, and if I were to take the median line right here, we'll call this 0. And then we'll say that any point of interest up here that we're trying to predict as a bright or dark spot will give the variable y, where this distance is y. Now, what that means then is that source 1 has to travel from this location to y, and source 2 has to travel from this location to y. So we'll call this one L1 and this one L2. Although those choices are arbitrary, these formulas actually have absolute values, so it doesn't matter. Now, if we take this length and we project it onto this other path length, such that this part and this part are equal, so we'll call that x and we'll call that x, then what we can see is the real difference in their lengths is just this little section right here. I'll call that L2 minus L1, and he's right there. So if we can figure out the geometry of this, then we can find L2 minus L1. Quickly, this angle right here is considered to be theta, and theta is y over L. Tan theta is y over L. This is the opposite side. This is the adjacent side. So if this angle, and I can't really see that well, let me just fix that there. If this angle is going to be theta, and we'll use that when we get into that little triangle, before we leave this big diagram, we'll say that tan theta is equal to its opposite side, y, over its adjacent side, L. So we have an expression for that angle. Now let's zoom in on this little triangle right here. So I have S1, S2, both of them are going off far away, and I've projected this one down, and this is theta, and this is 90 degrees. So we can sort of bounce around here and get some ideas, and I'll add this side here that's connecting these two sources. This length here, the distance between the two sources, we use the variable d, and this right here is the path length difference. We said this and this are equal in path length. So if this is theta, then this is 90 minus theta. And if this is 90 minus theta and this is 90, this angle up here is theta. You can go through your triangle laws or whatever to convince yourself of that, but right up there we have the same theta that we had down here. Now, this is a little bit tricky, but look at this carefully. The right angle's here. So this is actually the hypotenuse of this triangle. I know this is one of those ones where it's on an angle, so it kind of looks like it should be the adjacent side, but it's not, it's the hypotenuse. And L2 minus L1 then is the opposite side. So if I look at theta, I can say that sine theta is equal to L2 minus L1 over the distance between the slits. Now, here, as long as the screen is far away and the distance and y is relatively small, L is much greater than y, then we can say that tan theta is very small. Using that, we can make our small angle approximation. This is very handy in this case, and this tells us that tan theta and sine theta are the same for very small angles. As a quick side note here, imagine a very small angle. This will be our adjacent, and this will be our hypotenuse, and this will be our opposite. Tan theta is our opposite over our adjacent, and sine theta is our opposite over our hypotenuse. So the small angle approximation is saying that our adjacent is approximately equal to our hypotenuse. If this angle is small, that's pretty true. Doing all the vectors we've done in this class, we've seen this a lot. Imagine this number was 100 and this number was 1, then the hypotenuse, 100 squared plus 1 squared, square rooted, would be 100.005. So we're basically saying 100.005 is approximately equal to 100. That's what the small angle approximation is, and that's close enough for what we're doing here. Again, though, it has to be a small angle, which means L has to be much bigger than Y. When we set up this experiment, we usually make L sort of on the order of a meter, and then these Y's will be on the order of centimeters. So this is a pretty good approximation for this experiment typically. Now, if we go back, we have our expression for tan theta, y over L. We have expression for sine theta, L2 minus L1 over D. And what we do then is we have a nice expression for the geometry of this situation that will give us the path length difference. Now, if I take that back up to my conditions for constructive and destructive interference, I can come up with what locations for y I expect to see bright spots or dark spots or whatever I want. So let's go and do that. So y over L was equal to L2 minus L1 over D. So let's say I want to find a bright spot. Then I'm going to substitute L2 minus L1 with n minus 1 lambda. So that's equal to that. And so that formula would predict the location of bright spots. For destructive interference, y over L, well, let's go straight over here, y over L. Here I would substitute n minus 1/2 lambda over D, and that would get me my dark spots. And probably most interestingly, if I want to know what delta y is, this would be the distance between consecutive bright spots. I could find yi plus 1 minus yi, which would be equal to I plus 1 minus 1 lambda L over D minus I minus 1 lambda L over D. And so this would be I lambda L over D minus I plus 1 minus, sorry, let me just expand that out, lambda L over D plus lambda L over D. And then these guys would go away, and I could see that my delta y, or my distance between bright spots, is wavelength, length to the screen, divided by distance between the openings. And if you imagine doing this experiment, you'd have a screen here and you'd have bright spot, bright spot, bright spot, bright spot, this delta y. is actually the most useful or easily measurable thing. So there you go. That is how we relate the geometry of the Young's double slit experiment to predict the location of bright spots, dark spots, or the distance between consecutive bright spots.